Okay.
Hello, everyone. We have started our stream. It's nice to see you, all you guys, once again. And let's Sasha begin his speech.
Okay. Hi guys. Happy to see you. Okay, let me switch off. Okay. So hi. This is the today's plan, um, and we'll start with a bit of clarification of what this course is about. Then we'll move on to the to some actual information about Cascadeur. We'll see how such a basic thing as a hierarchy of objects, or what usually is also called parent-child connections between objects, how they work in Cascadeur, and you'll also see that they are very low level, and you can change basically everything you want in them. Then we'll move on. We'll examine it in more detail by creating our own very simple implementation of a hierarchy with parent-child connections. Then we'll look at a standard 3D node in Cascadeur. That's basically the joints and the mesh objects, how they are structured. Again, it will be about low-level implementation, but I think it's like to actually use Cascadeur, you like create your own rigs. You need to know this. Then we'll talk a bit about how box controllers and points are different from the standard 3D nodes. And as an interesting thing, as a teaser, I'll show you a teaser of segmental scale compensation, which I played with, tried to implement it. It was a request from the Discord channel, and that's the whole plan. So today I'll also be able to actually read your comments. So I've used my phone. So I'll be seeing the activity in the chat too. Okay, guys. So let's start. About the goal of this course, I just wanted to make a small clarification, as I didn't quite say it explicitly the last time. I think I talked that, like, I talked a little bit about what this course is about, but I just want to clarify in bigger detail that, this course is not like I'm doing the streams. I'm not like really rehearsing a lot before the streams. I do them pretty much as is. Of course, I do have a structure ready, but it's not a very polished and repeated many times videos as we have for our tutorials for animation, and that is because I think that to actually figure out how this works, how our rig works, to give you enough information to actually create your own rigs, and this is the goal of this course. It's first to give you enough information to be able to understand how our rig is structured, and that will also give you the ability to create your own rigs, to customize as much as you want. And second, for those who are interested, to give you a bit of an insight in how Cascadeur really works, what tasks are done right now, what are the limitations. So that's the main idea of this course, and why we are presenting the information in such a way is because there's just a lot of this information, and it would take too much time to create polished courses about it. We will update the documentation, of course. Maybe we'll even make some tutorials, but I think in a distant future. And on the other hand, I really do want to pass on this information, to share it. So I'm really happy that you're actually watching my streams. So thank you for this, and I plan to move on with this streams, and I plan to have a stream once a week for now. While we still have a lot of topics, then later maybe once in 2 weeks. So without further ado, let's move on to some actual information about Cascadeur. So, hierarchy of objects in Cascadeur. Well, in all the 3D software, in most 3D software, because there's certainly I don't know all the 3D software, but almost in any 3D software you have a hierarchy of objects, and usually what that means is that you can child an object, one object to the other, and first you see the hierarchy in an outliner. Sometimes it's called hierarchy, sometimes it's in Cascadeur it's called outliner, so let's stick with that. And then also, if you child one object to the other, then when you move this parent object, this is called the parent object, this is called the child object, obviously. When you move the parent object, the child object moves with it. When you rotate the parent object, the child object rotates with it. You can also, just to give a bit more understanding, I don't know, probably a lot of you are familiar with it, but this each object usually has a coordinate system that is, that is, when you select it, you can see this coordinate system if you use the translator mode. And then coordinate system obviously means you have some coordinates, and that if one object is a child of the other object, then the coordinates of this child object are calculated in the coordinate system of the parent object. So, but that's not a math class, so we'll keep it very abstract. I just wanted, just because I'll be using this words, coordinate system, etc. I just wanted to make this small statement, but let's move further and see what actually this parent-child hierarchy means in Cascadeur. By the way, you could say that Cascadeur is ideal for kind of studying it, because in Cascadeur you actually can see how this structure, how the structure beneath it, this parent-child connections actually works. But we already covered in the in the first part that you have some behaviors on your object, and among those behaviors you can see this basic behavior, and you can see here there's an attribute, a field parent in this behavior, and you can see that it's written mesh object 0, and you can press on it and it will select this parent object. So definitely one of the things that correspond to the hierarchy in Cascadeur is this basic behavior and its attribute, or its field. I don't know how to call them, but okay, I called them attributes the last time, so let's stick to that. The attribute parent. Although attributes are the nodes, so maybe I should call them fields. And let's just open node editor. Okay, let me select both objects, show them. And here in the node editor, you can actually see, by the way, this behavior. Where is it? Basic behavior. And you can see parent mesh object. Here it is. It opens the object. Unfortunately, by the way, I saw that there's a bug that prevents us from setting objects for the fields in behavior editor, and behavior editor is this left part of the node editor window. So I won't be able to demonstrate it. It will be fixed by the next version. But I wanted to demonstrate one little detail about this node editor and behavior editor. There are times when you want to set something into this object, but this something is inside the other object, and you kind of select the other object when you actually move to it. And so you don't know how do you set a data of mesh object 0 to some field in mesh object 1. And to do this, you actually have to click on this little lock right here, and then after you click on this lock, the selection doesn't matter anymore. You will always see the object you saw when you pressed the lock. So it kind of locks down this behavior editor to this object, and so you should be able to basically switch and set a new object here. But unfortunately, right now there's a bug, so we can't do that. But never mind, we will do a different thing then. We can also see that between this parent object and this child object, we have some connections. So one thing is what we have set in this behavior. Yeah, let me just say what systems actually look at the field in the behavior, at the parent attribute in the behavior. Okay, let's stick to the attribute. First, and the most important probably, is the outliner. You can basically child any object to any other object, and sometimes the only thing that changes is this, is how you see the subjects in the outliner. And this is sometimes really handy. For example, we have a rig, and inside we have all the objects grouped by their type inside the rig, so we can see all the edges. And for edges, for example, it basically doesn't mean anything. Edge is just a connection between 2 points. They're not in any other way connected other than through this attribute, but it keeps the system systemized, so it's convenient. You can also select objects by double clicking because of the hierarchy. And so different support stuff like that and organizing stuff is connected to this behavior. So then what about this motion that we see when we move the parent object? The child object moves along with it. So what does this, where does this come from? This comes from the fact that they are connected inside the node editor. You can see these connections, parent rotation and parent matrix. Input attributes are connected to rotation and matrix output attributes of the parent object. And this connection is actually what makes the update work in such a way. We could actually just connect this thing differently. For example, connect these two attributes to the output attributes of mesh object 2. And now what we'll see, you can actually, it actually changed its position. mesh object 1 is childed to mesh object 0, but if I rotate or move mesh object 0, mesh object 1 does not rotate or move. But if I move or rotate mesh object 2, it will behave, mesh object 1 will behave as its child. So, yeah. You could say we kind of broke the Cascadeur, but that's actually how this works. And again, because this is so low level. So let's try implementing our own objects that are connected, that can be connected by hierarchy and will actually behave in a similar way as the cubes we saw right now. Okay, to do that, we'll open node editor, and again we'll create a point. And inside we'll create a position. And we'll add some behaviors to it. We'll add a transform behavior. We'll add a point behavior. It already has the basic behavior we plan to use for creating parent-child connections. So let's set position as global position, and as the last time, we now have a point. It looks like a point. It moves like a point. So now we want this point to be able to be. We want to be able to connect such points as parent-child objects, and we want for the child objects to move when we move the parent object. We won't be able to rotate them, but we want them to move accordingly. Right now, if I just duplicate this point, child point 0 to point, move the point object, nothing happens, and that's because like it's not connected anyway in the node editor, so they just have a position. The translator just changes this position, and that's all. So okay, we want the child point to move when we move the parent point. What does that mean? That means that we have, of course, we need to have the global position to actually see the point in the global coordinates. But if we wanted to be able to stick to some other point, it needs to have some additional data of how it is positioned relative to the parent point. So let's create a new vector3f data and call it local position. And now we'll have this, we need this parent position and we want this parent position to be summed up with the local position, and that will give us the actual global position that the point has. Okay, so let's create a new node, regular function. It will be a sum of 2 3f vectors. Let's activate it. Now let's also connect this local position, set this local position as local position in the transform, so we can see it in the outliner. So now actually if we try to move the point, okay, where does it move? It actually moves. It's pretty interesting. It doesn't seem to be connected. Interesting. Now that looks like a bug. I don't. Oh yeah, sure. It still doesn't work, and that's not a bug. Okay, maybe I have to practice more. You can see that this function is still not active. And why is it not active? Because you can see that this yellow connection, it actually, if it's yellow, it means it's actually not connected to anything. So it is just sitting here and doesn't have any value bound to it. So let's put some value, zeros, and now we can see this function is actually active. It's a bug that this is still yellow, but never mind. So now it jumped here to the, basically to the 0. Let's make it real 0. And what actually happens is that we can't move the point now. I try to move it, it stays in the same place. Why is that happening? Well, because right now the global position is always controlled by this function. So what I can change is the local position. I can change it here so you can see the result. So I can change it, and it actually moves. But I can't change the global position. Well, that's a shame, but let us just try out. Let us just see if the hierarchy will work itself, and then we'll make a mechanism that will allow us to move the translator. And the translator itself always changes the global position. That's actually, our translator always changes the global position and the global rotation. That actually prevents you from adding rotation along an axis, which is not such a nice thing, and we plan to extend our translator rotator capabilities. For translator, it's okay, totally fine. Okay, let me just hide this. We don't need it right now. What I wanted to show here is that even with this, our parent-child hierarchy will already work. So if I duplicate the point and child it, and let me set some local position. Oh, it's already set here. Okay, so I can change the local position of point 0, and if I change the local position of point, then point 0 will move along with the point. Again, why this happens? Because now I have point 0 and it is connected. Of course, it is connected via the behavior, because that always works, because everybody has basic behavior. But what also happens is that when you child one object to the other, it searches. It works. It works very in a very simple way. It's structured in a very simple way. I'm actually even a bit shamed that it is such simple, but it works for now. And I was thinking that maybe we will change something in the future. But for now, all parent-child connections bindings we had, they all work perfectly fine with this system. So I don't know why we would have to change it. Maybe we will, but for how the system works, it basically goes through the input attributes, searches input attributes that are named parent white space something. Then it goes to it does it for the child object. Then it goes to the parent object, and it searches for the output attributes that correspond. If you remove this parent white space, you have something left. We go search to the parent object. We see if there's an attribute that is named exactly as what is left, and it just connects them if it has such an attribute. All this logic is actually inside a Python script that always gets called when you create parent-child connections between objects. So you can basically change how parent-child connecting works in Cascadeur. Yeah, and by the way, I'll look at the chat. The node is neutral. Yeah, thank you. Okay, so yeah, it's simple, but personally I think it's fine, and we'll see how it goes. But again, you can change it. You can actually change it in your own version of Cascadeur. And I think at some point of time we'll look at this parent-child connecting script. Although it's big, we'll just have a very little glance at it. Okay, so now it works. The problem is you can't move the points, and you also can't copy-paste their global coordinates, and that's a problem. So let's create an upgraded version that you can actually move. Okay, this will be very close to what we did last time. So what do we want? We want to be able to change the global position, but of course we still need a valid local position. So when we can grab the child object, move it, and then we go grab the parent object, move it, and child object moves along with the parent object. So we already need the correct local position for the child object. Hope you didn't get confused here. It's a bit hard, but let's create it. And of course, how do we calculate local position? Well, we just subscribe parent position from the global position. Wait, oh, sorry, subtract. Okay, so from global position, we subtract parent position, and we get the local position. But of course, we can't turn it on because there will be a cycle then. So when does this function activate? Well, it will activate. To do that, we'll have this setting function. It will activate. I'm sorry, I can't turn it on yet. It will activate when this global position is changed. And we call it actuality, and this is it gets actual and it gets changed. When it gets changed, this will give a true, and then this node will activate too. And when it's not changed, then we turn on this one. So now we can turn this on, and we can go select, move the point, and it works. So we can change the global position, and we can change the local position, and it always looks as if they're always the same, because it doesn't have any parent. But let's duplicate it, child it. Now we can move the child, and when we select and move the parent, the child will also move along with it. So And this is basically how local data works in any object. It's just that here, like the only data we had was position, so we didn't have any rotation. So I select the parent and try to rotate it. Okay, it even says that this object doesn't support global rotation around itself. I still can select both objects and rotate them, and the rotator will just calculate the global position for this object, but that's not the same. That's not quite the same. But that's basically how this transform works. Let's just have a final look. So here's the point 0, and they are connected. And you could connect several points. I don't know. Okay, I don't think we have to create them and stuff, but you can make several points, child them all. There will be a connection like this one, and here it will calculate. Okay, we can turn this mode on. Then we see only the things that are actually active right now. So, for example, here we see how it gets calculated. And if okay, that's certainly a bug. And now you can see that it's calculated the other way around when the global position is changed. When I switch here, when I turn on the switcher, it basically means it simulates the situation when this data was actually changed. And if I actually change it, it does it, but like behind the scenes, you can't see, so it can be turned off. And it can be turned off, but you can still change it. This is like a virtual thing, just to simulate and to let the user actually see how the graph will look like if this data gets changed. Okay, so let's just look at the chat. Okay, doesn't seem like we have any questions in the chat. So let's continue. Let's now look at the standard node we have in Cascadeur. Just create a couple of joins. I don't know why not cubes, but joins seem simpler to me in some way. And let's look at them in the node editor. And now, as we know the simple example, we looked at this simple example, we can understand how it works here in a pretty complex example of the standard 3D node. So you can see that it has 3 incoming attributes that are marked parent. This parent inverse matrix is also connected to the parent inverse matrix, obviously. So that's the information it receives, the child node receives from the parent node. Okay, let me zoom in. And yeah, by the way, we didn't cover it in the last tutorial because we were creating always very, very simple nodes, but actually when the node is pretty complicated, when the structure of the object is pretty complicated, you usually group a bunch of datas and functions into a group node, what's called a okay, how do we call it? Call it a group. Yeah, it's just a group of nodes basically. So this blue rectangles that represent groups of nodes. Let's just jump into one of them. So here's what is inside of this node. There are 3 nodes that basically calculate some setting stuff. They decide what data will update by what data. And let us just look through these nodes. We can see the local group, and this local group basically it consists of 3 datas that represent the local transform, the local coordinates. It's the local position, local rotation, and local scale. Yeah, and if I show all the nodes that are in here, there are also 2 functions that calculate local position and local rotation from the global position and rotation. And then, of course, in the global group, we have the global position and global rotation, and the functions that calculate them. Actually, a small setting function, we had it there too. It's a setting function that basically tracks if any of this data was changed. So if any of this data was changed, then global data are actual right now, and they pass on this as this function passes this on, and then other stuff, other setting functions actually decide how will we structure what we will turn off and on in the graph, in the data graph. And then we have this node matrices, because an actual 3D node is based on matrices. Maybe I could go in one of the lectures through the basic math that is that there is, although okay, I'm not very confident as a math teacher, but it is easier to understand what these matrices mean, how they are how we multiply the matrices, why there are 4x4 matrices, etc. So basically we calculate this local matrix based on the local position, rotation, and scale, and then we multiply the local matrix and the parent global matrix, and we get the global matrix of this 3D node joint in our occasion. And then we also calculate inverse matrix, just so it's something like a cache, because we want to calculate it only once, to be calculated only once. We don't want to inverse this matrix. If we have several children, we don't want each of the children to calculate this inverse matrices. So okay, so and yeah, and then this node here is the decision-making node that actually tells these 2 nodes basically which of them works. We can see that the matrices are calculated always. They're calculated like the last. They don't. You can't enter value into this matrices nodes. So we can actually open them, but we can't. If we try to set them, they will be recalculated. They will not affect anything. By the way, why don't don't they get recalculated? Okay, that's strange. But let me move it, and we can see that they get recalculated. Yeah, so those get recalculated. You can't enter matrix values, and but you can enter both local and global values, and the switcher will decide how what we will calculate, whether we calculate local values based on the global ones or the other way around. And we also have this IK behavior. I think you also have it here. No? We don't have it here, but you can't switch it. And if you switch it, then when I move the parent object, the child object will stay in place, because the local values of the child object will be calculated based on the global values. It's just not put into this interface. I don't know why, but probably nobody needed it, but we do have this setting. Okay, so that's how this standard 3D node transform in Cascadeur works. Let me see if there are any questions. Maybe a dumb question, but what's the practical use for the locator? How can it be used in the scene? Well, usually it's either used as a controller and you child something to it, or you can use, I don't know, just to put a pivot in some place to have your, I mean, like a, for example, create a locator. You could use any object for that. The locator is just kind of better suited for it, and then you right click on the locator and you can rotate around it. Those are the main examples. Okay, so I don't know how deep it will be better for me to go into this topic of the standard 3D nodes. Please leave comments if this is understandable, if it's too fast, if it's too slow. Maybe I can just go through faster, but yeah, have to pass this, want to pass this information on. Okay, let me just talk a little bit about box controllers. So how they are different from the nodes. Let us select a pair of box controllers that are childed to each other. I don't have any. Open the node editor to see how they are connected, and we can see here that there's a parent position and parent rotation. Unlike the matrices in the 3D nodes, for box controllers, we only have position rotation that is connected to the parent position rotation. And inside, we can actually see that there's this node that actually does some additional function. It connects the box controller to the joint. And this node that is called ortho transform, this node is the one that holds all the transform logic for the box controller. So this node, it's actually much more simple. So it's not even, it doesn't have some subnodes because it's so simple. We don't have any matrices. Basically, we have just local position, local rotation. We don't have local scale, and that's what allows us to keep it very simple. Actually, if you have scale, you can create with the combinations of scale, you can create transforms that can be described only via a matrix. So you can't describe them with global position rotation or any global scale that you can kind of imagine. You need a matrix to do that. So at least I didn't see any systems that would be like that. But if you don't have scale, then everything gets much simpler, and you can just combine, transform parent position rotation and local position rotation, and get this global position rotation, and you can do the inverse operation and actually calculate local position rotation based on the global position rotation. And it's really a simple operation. You can try to decompose the 4x4 matrix for transform, but it is a very cost heavy operation to do. Okay. But you can see there, it has much more settings, by the way, because it can read IKFK from timeline or behave differently on timeline and when editing in the frame. So there's a bunch of settings for box controllers. And for point controllers, they're actually quite custom. One thing that is done for point controllers is that by default, when you change the position of the point controller, the child point controllers, they're not moved along, but we do have a setting here in the point local controller that is called FK on frame, and if you turn it on, then the setting graph logic works differently, and they actually move along when you edit their parent. They move along with the parent, although it doesn't work ideal. Okay, yeah, because this one was in IK mode, but if I put it to FK, it should work better. Otherwise, I'd say, just to not jump into some details, that they are more complicated and more custom, and different points have different local data. For example, a twist point like this one. Okay, let me turn off this FK on frame. So a twist point like this one, it has its twist as the local data. And by the way, they also, instead of global position or global rotation, most of the points have global vector direction, I call it direction usually, as their IK data. And that works different from position. Maybe we can cover it in a separate lecture, or in a separate stream. But my streams are like lectures, so okay. So let's not jump into it too much. I think that we will cover it in the future lectures. But by the way, in the very end, okay, let me see how far we got. Okay, we're basically here. I think that we'll have a bit of time in the end to just talk about what other topics we have, and then I'll ask you to just okay, maybe we will make how do you call it, like a questionnaire about what topics should we cover next. But okay, we'll get to that in a moment. And now let's have a little teaser that is not as complicated as the point system, and it's the segmental scale compensation. So what it is, and why do we want it, and I'll also show the implementation. I have already showed it in the Discord chat, but I'll show what I actually did to achieve this segmental scale compensation. Yeah. So let's let me cover in just a very broadly. Sorry, create a new scene and import. This one. So right now, how the scale works. If I scale an object, then obviously all the child objects, they will inherit the scale. So suppose I scale this bone, all the other bones actually scale. Scale this one, they scale and their position scales, and yeah, that's how it will look like. The problem with this is that when you have an IK over top your joint rig, it will limit the positions, the change of the positions in all the bones, and it will look pretty funny, I would say. Okay, let me just scale it here. This seems to be odd, although it's not really what we want. But if I try to do this, they will just drown inside of themselves. Yeah, and it will actually, if it's not symmetrical, then it will look very strange. I move and the shape will get different. So it's really hard to connect this scale that works for the whole hierarchy with the IK rig that controls the positions and rotations of the joints. So what is usually done to let users control the scale is what is called segmental scale compensation. That basically means that you scale one bone and none of that scale goes to its children. I have to say it's not implemented in all the 3D software. As far as I know, of course I don't know all the software, but as far as I know, it's implemented and was probably first implemented in Maya. I know it is implemented in Unreal Engine, and as far as I know, it is yet not implemented in Unity. And about Blender, I'm not much of an expert there, but at least as far as I know, it's not implemented out of the box. Maybe you can do something custom. Maybe you will correct me in the chat, but or in the comment section. But as far as I know, by default, it's not possible to do that in Blender. But I think you can customize anything you want in Blender, so probably there are some plugins or settings, or maybe they included it already. So yeah. Now, how this segmental scale compensation works? Well, let us first write just a bit of stuff to understand how you generally compute the matrices. Well, as we already saw, the global matrix, it's the global parent matrix that is multiplied on what I call the local matrix. But now you can create a local matrix out of position, rotation, scale, but you could also you can any of these transformations of the space, like the position. Okay, I'll call it translation. We call it position here as we call it in Unity to just keep it simple. But yeah, I would say the more correct term will be translation. So the translation, the rotation, and the scale, each of these deformations of the space could be represented as a 4x4 matrix. Yeah, I really I'm really tempted to jump into the math of this because it's really nice. You could say somewhat crutchy. Some say it's somewhat crutchy, but I think it's also an elegant way to present all this stuff. So you can represent them as matrices, and it's easier for us right now to represent them as matrices. And I would say that basically you multiply to the translation, you multiply global parent matrix to the translation matrix, and then to the rotation matrix, and then to the scale matrix. I think it has kind of an acronym TRS, so it's always translate, rotate, scale. Now, what do we do with this segmental scale compensation? Well, of course, this parent matrix in its own place, it's connected. It consists of its own global parent matrix and its own translate, rotate, and scale. And what we want to do with segmental scale compensation, we want the scale of the parent not to affect our children, but as the scale, it will affect. But of course it has to affect something. If we just add it and remove it, then it won't change a thing. So it has to affect something. It's also connected to how points are points of the mesh, how they're skinned to the joints. But without getting too stretched, just let me say that we wanted to affect our own translation, but we don't want it to affect the rotation and scale that will in turn affect the translations of our children. And that's why you place an additional multiplier here, and it's the parent scale. Inversed. And by adding this inverse parent, you actually neutralize the rotation, and you neutralize the scale that the parent has. And if everybody does that, then basically this scales, they don't affect anything but the object itself. So that's basically it for the formulas. Now let's see how I implemented it. Okay, so we'll have to open my own version of Cascadeur. Not sure I got everything ready here. Okay, it seems like I've got everything ready here. Let me just confirm. I have the latest build. Okay. This one. Oh, that's the original. One second, sorry. Because I was kind of implementing the sequential scale compensation, I checked out the different version, but I think it will be pretty fast to resolve it. Okay. So again, let me just create a couple of joints, child them, hope everything is correct, but we'll see in a second. And now if I go here, node editor, you can see it's a bit different. There are now 4 connections, and one of them is the parent inverse scale matrix. It's this thing that we also get from our parent. And inside the matrices section, you can see that we also read this parent inverse scale matrix, and we also output our own inverse scale matrix. And here what I do is I construct this rotation, translation, rotation matrices and scale matrices. How I construct them with this compose node that basically it takes in position, rotate, and scale and creates a matrix. I just set identity rotation, identity scale, which is 1, 1, 1. Here I set 0 position and identity scale, and set rotation, and the same for scale. And I now have 4 matrices. Actually see how they. Okay, let me rotate and scale it a bit, so you'll see how it's different. I know you can't see it on the joint, but we'll just see it on the matrices. So should have great cubes, by the way. Then you will be able to see it. So the rotation matrix looks like this. The scale matrix is a diagonal matrix that looks like this, and we have some scale here. And so then all these matrices, they get multiplied in the same way as we wrote here in the formula. And thus we calculate the global matrix, the inverse global matrix, and the inverse scale matrix to pass on to our children. And by the way, when I import from FBX, then all the 3D transforms are created from scratch. If I create 3D transforms, save them to a scene, and open that scene, the scene already contains all this nodes. I mean the nodes from the node editor. Okay. Sorry, I have too many versions of Cascadeur. And that's why it won't update automatically. So if I change how the standard transform node looks, it won't actually update automatically. If I open an old scene, I have to create these objects from scratch. And one of the ways the easiest way to do it is to export to FBX and import it back. Okay, and so now I now I showed how I did this. No, sorry. Now let me show what that actually means for a real character. That means that when I turn on the scale and change it, it will only apply to the points of the mesh and to its child, but the children joints, they will not be affected by the scale. And that allows us to actually work, although it's not debugged yet, so it had the rigging tool was not ready for this. So let me just open the scene where I'll have everything ready. Yeah, that's the scene. Here I actually binded scale to the length, to the deformation of the length of this edge. But I've only this for this edge, but that actually means that I can come here, scale, and I will scale. You can see it scales, but only within this joint, so it doesn't affect any other joints. And this is actually, this can be usable with an IK rig on it. This as far as I understand it. So, oh, sorry. I don't yet know how to let users control it. Maybe they can change to scale and scale each part, like, and when they scale the point, they will actually scale the joint that corresponds to this point. Or maybe there are some other ways. Would be great if you wrote them in Discord or in the comments. So, oh, I see we have a question from Quicksilver Sash. What happens if I scale all the joints? Okay, let me scale all the joints. I'm not sure, by the way. I think currently our scale tool doesn't like it doesn't work in such a way. If you select several objects, I'm not sure it changes the scale of all the objects. I think if you select several objects, or maybe it does, I don't know, but it will change them in a pretty strange manner, I think, because it's not like tail mode. It's not like I scale. It will probably scale them in different ways. Starts to scale fingers. So if I scale them here, for example, I can change the width. But if I scale it like here, I can change this width. But if I select them all, I think to do that with the result that I would expect, we need to have something like a tail mode scaling that scales each bone in different directions, because for these bones the X is one thing, for other bones it's other thing, and I'm not sure how it actually works right now. There's a question from the chat, and will this always be done for the bones directly? I'm not sure. Here's something I proposed, that deforming the length of the box of the point controllers will change the scale, but I'm not sure it's what we want. So I don't actually have a concrete plan for now. We will have segmental scale compensation in the next version for sure, but how will we work with it and what's the plan, we're still kind of figuring out. Okay, another question. Also, would there be a way to scale on all axes at the same time without using the object properties panel? Scale on all axes at the same time. Yeah, I mean, I'm not sure you can actually do that in the properties panel. You probably can. Yeah, you can do it. But yeah, that's what I meant by something close to a scale tail mode. You know, when we have a tail mode in rotation, and when you use it, it basically means that each of the, oh sorry, I didn't turn it on. Yeah, if I don't use it, then everything gets rotated in the same way, on the same angle, and I think that's what happens with scale. But if I turn it on, then each object rotates by its own x-axis. So you can see how the pose changes. So I think if we do that, it will provide us with the ability to scale the whole character in some axis. Okay. So for the point control, from the chat, Solid Cloud, right? So for the point control, dragging out to scale, would this be toggle switch we'd enable? Yeah, maybe. I'm not actually sure about this idea of mine for expanding the scale, looking at this edge, because one of the things people want is that when you actually stretch it, the mesh kind of tries to keep the same volume, and to do that you basically have, like, for example, you scale by x-axis, like suppose you have scale 1 1 1, and then you stretch by the x-axis, and that means that it's longer now by the x-axis for some amount a. And what you can do is put this scale a here for the x-axis, and put the scale for the other axis, and then like more or less the volume will stay the same, approximately the same. That is done a lot in this rigs. Okay, Solid Cloud, or would the default behavior be to scale them if that is set up? Yeah, I really don't have an answer to that. I didn't decide yet what would be the default behavior, and I would be happy if we talked about it with you guys, because advice would be it's something that the users should actually decide. Of course, we will talk with our own animators, but if you have an opinion on that, I'll be happy to hear it. Right, so if we want to scale instead of keep volume, a toggle might work, sort of like the R button for the relative. Well, yeah, maybe. Although I'm a bit afraid of overloading the rig with different buttons, but maybe we can do that. Wouldn't scaling Quicksilver Sash, wouldn't scaling by extending points mess up stretching fulcrum K? No, at least as far as my imagination goes, and as far as I see the technical situation here, no. By implementing this segmental scale compensation, we kind of now you can scale any joint without changing the position, and it will not affect any other joints. So we actually can combine and just control the scale as we want it. Solid Cloud, I'm done for chat with you guys. I'm down for chat with you guys. Thank you. Yeah, so let's chat about it. It would actually be nice to maybe sometime have a call in Discord, because I think it might be easier when we just hear each other and talk about it. So maybe at some point of time we will have actually a stream just to record the information, and we'll also meet in the Discord as we. Right now we're on a Discord call with Ilya, so we can both like participate. Ilya, by the way, are you here? Do you hear us?
Sure, I'm here. Sure, I'm here.
That's great.
Yeah, and I think that we can arrange it in couple times per month. We had an idea to show some progress of our development, and we can gather feedback internally.
Yeah, although topics like this one will require a lot of time for us to talk about, but it would be interesting. So that was the teaser of segmental scale compensation. I think I answered most of the questions, and it's a teaser, it's not ready yet. So yeah, just wanted to say what other ideas I have for future topics, and maybe you can write some additional ideas. So one of the ideas I had is that we go through the whole Cascadeur rig, and then maybe even follow the rig creation process, look at the scripts, at how the rig is connected, what it consists of, etc. So you could understand our rig better, and maybe have some ideas of what we can add to it, or maybe add something yourself. We will cover some, I said it's a separate topic, but it's actually belongs to some list. We have some additional features like dynamic behavior. So while we're at covering the rig, maybe we will look at what is dynamic behavior, for example. And it's a pretty simple thing. Okay, positions and directions. In Cascadeur we have some of the points of the control rig. Their IK data is not a position, it's not global position, it's a direction. And that means it behaves differently in interpolation, and I think we have to cover that. And we use a pretty special interpolation, so it would be interesting to cover what math lies behind the Cascadeur rig. It's pretty custom, and I think that could be a lot of fun. IK data in our point controller rig, yeah, that's what I actually just told, and how it interpolates that. Actually, we could also cover FK data in our control rig, because it's not trivial too. It's pretty custom. Still not sure it was the best solution, but it's pretty good. It has its advantages, so it has its pros and cons, and I will be happy to cover it too. And then concrete implementations that were requested by the community, like look at constraint, a wheel constraint that basically you move an object and something rotates. We could just I could implement that, and we could then on a stream see how that was implemented, or maybe even implement some of that ourselves on the stream. Okay, so these are the ideas. I think for now I will mostly stick for the rig generation process, but if it's not that interesting, please write in the comments, write in the Discord chat, and yeah, everything can be discussed and we can change the plans. So that's it for now. Thanks a lot, guys. Really enjoying it, actually. Thank you for the questions, awesome questions, really deep understanding. So I think let's call it a day. Thank you. Bye.
Thank you, guys. Bye, and see you next time.